physical if you didn't write it down last time on your assignment packet. Do you feel like you can calculate the heat exchange and reaction using data from calorimetry? So that is calculating Q. Do you feel like you've mastered that objective? Do you feel like you need more help with it? Where do you feel? Give yourself a quick marking. Once again, if you find yourself marking in the boxes of I can't do this or I can only do this with help, my first question would be to you is, okay, have you done the homework? Homework is there to build your confidence in the skills that you know how to do it, right? Then, if you still need support, come see me. Another great support that is available all times, because I'm obviously not here all the time, AP Classroom has topic videos by topic, right? So if you put, hey, I'm struggling with 6.4, go to AP Classroom, pull up the 6.4 video. They're often not super long, and that could be a great way to maybe fill in if there's things that you weren't quite understanding, okay? And then 6.6 is our understanding of enthalpy, and then calculating it, which is where we did Q over moles, was calculating enthalpy, okay? Our first objective today is using heat in relation to phase changes. So still on the category of delta H, but now instead of a chemical reaction, we're looking at it in terms of just phase changing. So let's take a minute. We're going to fill in this phase diagram. So phase diagrams are the same for every substance in shape, but the length and height of things would change. So like, I don't know, I think this one's for water maybe. But if we did a phase diagram for, I don't know, pick another substance, gold, it would have this same shape, but obviously the numerical values would vary. Okay, so the starting point of our phase diagram, okay, looking at our axes here, the x-axis implies it is constantly being heated, right? So let's say water, simple example, I have a beaker full of ice cubes is how I'm starting. I turn on the heat and I don't turn it off. The y-axis is a thermometer that's in that beaker and it's measuring it constantly as it goes. Very boring experiment because you simply are just measuring as it gets to boiling, but the data is interesting, okay? So label this first box here as our solid state. Okay, so this is the point at which it exists as a solid. Notice that this point on our line is a range. Okay, right? It's not a single point, but it's constantly changing because things can exist at a solid at a lot of different temperatures, right? Like the ice in my freezer is not at the same temperature as the ice in Antarctica, but they're both ice, okay? Whenever you're on a diagonal, this is where MCAT comes in. We could use the MCAT equation to see, hey, how much heat is it going to take to heat my ice from -10 to -5? Okay, but whenever you're on a diagonal, that's when the Q piece comes into play. All right, now notice the temperature plateaus out during the phase change. So from going from solid to liquid is called melting. Going in reverse would be called freezing. Okay. Now, why though, if it's the beaker is still on the hot plate, we're not taking it off at all during the experiment, why is the heat not going up? Why is it, sorry, not the heat, why is the temperature not going up? Heat's going in. Where's it going? Why is it not heating up, AJ?
From what I understand, it's going into making breaking the bond between the molecules.
Perfect. The IMFs, yep. So all the energy at this point that's being put in is being used to break them apart. They can't start moving faster until you unlink them from each other. So that's why while it's melting, the temperature will not go up. It's going to stay flat. For water, it would stay at 0 Celsius. Once it's all melted, now the water can start heating, right? So this would be our liquid portion of our line. Once again, we have another diagonal, so Q would come into play here. Oh, let me back up. The plateau portion doesn't apply to Q because temperature's not changing, but it does apply directly to delta H. This line right here is called the delta H of fusion. I don't really know why I kind of know why they picked that word, but it'd been nice if they just picked an easier word because fusion has multiple meanings. But you can think of fusion as coming together, but it also applies to it coming apart to just this sign change. Yeah, let's see.
What is it direct, like, relate, how does it directly relate to that age?
Because at this point in time, because Q has a temperature change, right? But at this point in time, the temperature is not going up. So the questions would be, and we'll do it in a second, would be along the lines of how much heat does it take to melt, let's say I want to melt 50 grams of ice. I would then use my delta H to figure that out. Because I'm not wanting the temperature to change, I'm wanting the phase to change. Does that kind of make sense for now? And we'll do a problem on the next slide that kind of shows that. But good question. I have a smiley face for that, Leslie. Okay, once again, we climb. For water, we'd get to 100 degrees if we were at sea level, and it will start to vaporize or boil, depending on how you want to look at it. Okay, so vaporization, the opposite of vaporizing would be condensation, condensing. Okay, so this is known as the delta H of vaporization, is what we call it, and the delta H of condensation would just be opposite in sign. And then once our water's all melted, not melted, water's already melted, vaporized, right? It gets turned into a gas, and then of course that gas can get hotter and hotter and hotter. Yeah, Stephen.
How would this work for sublimation?
Sublimation's an interesting thing, and it's kind of like, it's dependent upon substances and conditions, right? So like certain substances, just that's what they do is sublime. That's a good question. I should look up the phase diagram for carbon dioxide. I don't know, Stephen.
Well, it depends on like the actual pressure of the surrounding pressure.
Right, and that's the thing is like everything could sublime under, but certain things at room temperature sublime, right? Like iodine sublimes, carbon dioxide does. But I don't know exactly. It would still have like climb, plateau, and things, but I guess it would just skip the middle portion and not have a flat out in the middle.
Also, if you went past gas, would there be another plateau and then plasma? Would it just keep going up?
Yeah, I guess assume we don't ever like work with that, so we don't really have a measurement value of it. But yeah, because the same thing, it's going through another phase change, so I would assume so. Yeah, Marilyn.
So you see that during the first phase change, the IMFs are breaking. What happens during the second phase?
It's still actually somewhat of an IMF break because solids, right, are just very hard linked IMFs. Liquids are like somewhat linked IMFs, and then gases don't have them at all. So that's often why you'll see, it doesn't show it great on here, but on some graphs, you'll see this line is a lot longer because it takes more heat to break those second IMFs than it does the first, depending on the structure of it. But yeah, good question, Marilyn. Have a smiley face for that. Okay, let's look at the math side of it. Okay, so our question says we want to calculate the energy needed to vaporize. Our first one is 15 grams of water. So the first thing you want to recognize here is what phase change are we dealing with? So we're dealing with vaporization. So of the data given up above, I only care about one of those H's. Which one do I care about? The vaporization one. In our case, this one would only apply if we were dealing with melting. I put it on there because on your homework, you're going to use both of them. So just pay attention to what the question's asking because it'll help you know which one you're using. If you're talking about melting, then you're going to be using fusion. If you're talking about vaporizing, then you're going to use the vaporization one. Okay? And then at this point, it's stoichiometry. So I'm going to take my given thing. So I'm starting with 15 grams of H2O. I need to convert grams into energy, which is given, notice up here, that's what this is, grams to joules, right? And joules are a form of energy. So I'm going to put, like a good stoichiometry student, I'm going to put grams of water on the bottom. I'm going to put joules on top because that's what I'm converting it into. The relationship is that 230. Oh, black on black is not going to work. What am I thinking? 230 to 1. Plug it into my calculator. And I got something. 34950 is my raw answer. Oh, that's not a 4. Okay, 34950. How many sig figs do we get to keep? I guess technically 3. So I'd probably write it as 3.50 times 10 to, not to the negative, 10 to the positive 4. You don't have to put things in scientific notation, but that's how I would write my answer. Questions on how I got it? Yeah.
What would the unit be?
Oh, thank you. I left off my unit. How dare I? What do you think, Michael?
Well, I mean,
Mhm.
if you wanted to, could you just write it in kilojoules?
Totally. Yep.
Okay. If it
Yep.
doesn't specify.
If it doesn't specify, you don't have to, but it wouldn't be wrong to do it. So, yeah. Which honestly, with a lot of these, because joules is a small measurement, so our answers are going to be very big. So it's often logical to put it in kilojoules. But. Okay, any questions before I have you try the next two for smileys? Yes, Steven.
Did you put it in scientific notation because it worked out easier? How long?
Yeah, and sig figs. It was really mostly for sig figs in this case, because I needed to show 3, and that 0 is hard to show that it's significant without it. So. Okay, I'm going to give you 4 minutes to work as a table. Try B and C. Pay attention to your units. You might have to do a little pre-step before. Sorry. Not sorry. Okay, ready, set, find some answers, go. 1,000. Anyone need a calculator today? We have a lot of math.
Is it over 4? It's decimal wise, like this will correspond to. It's just
Yes, it is 1,000 grams. 3 decimals. 1,000 grams and 1 kilogram. Everyone need a calculator today? You don't want it because everything we're doing has a math. Anyone else need a calculator? Once your table all agrees on your answers, change your lights to white and I'll come check it.
Moles? Whoa.
Once again, once your table agrees on your answers, change your lights to white and I'll come around and check it.
Are we supposed to do the C?
Yeah, do B and C. Question, Henry?
I got this for the.
Good, to change it into grams. Good.
Then what do I do next? So I multiply this by that.
Yep, so this, because this is grams, and grams is on the bottom, and we're trying to get into joules. So yeah, that times that.
I did that and I got this.
That's your answer.
Just that? That's it?
Yep, that's it.
Times 10 to the 7.
What's the nutrient?
1.34 times 10 to the 7.
I said 13.20.
This is for the second group. So 5 and 5 kilograms. So we only have to figure it out grams. I didn't put my note.
I got 13. Did you divide it by 5? 69.
Water does 1 mole of water does not weigh 69
Divided by
grams.
1,000.
Tell me.
What's going to be your starting piece? That will help. So put that out front. What's the unit with that? Which then means what unit should go on the bottom.
Wouldn't it be 1 mole?
Good. And then what's going to go on top?
Grams.
Good. And how do I find the grams of 1 mole of water?
I used to know this.
You got it. You got it. How do I find out how much 1 mole of a molecule weighs? There you go. Good. So add up your water. Yeah.
Why did you put tenths before power?
I just changed it to scientific notation. So scientific notation is just where you move the decimal over. Does that make sense? So they're the same. It's just a consolidated way of writing it. But you don't have to do it that way. It just, when you have lots of digits, it can help. So thanks, Rachel. What do we think of our new beachy tune? Does it feel nice for, for like February, January, February months, like a little more lively? Okay, give me a fist if you're ready to check. Give me if you need 1 more minute, give me a, are we ready to check it? You're supposed to change your light to white when you were ready.
I'm ready. Everyone else.
That's fine. Okay, we'll give 1 more minute and then we'll check it all together. I'll just come around and check. Oh, you haven't done C yet. Do C.
Okay, so moles.
Those look good, guys. Have a smiley face.
Usually find out what the atomic mass is.
Same Wexian. Good.
I thought you did C.
I have an app for Python.
Yes? Yes. Have smiley faces all around.
How many? 2? Wait.
2. Answers are? Oh. I can't find them on Gavin's paper. Yes, good job. Have a smiley face. Do we have answers? Good job. Have a smiley face. Keep going, Michelle. You're good. You're good. Good job. Have a smiley face. Oh, I went too far.
Times 23.
Everything is legal.
Yes, yes. Good job. Smiley faces all around. Oh, yours is hanging on to its last life.
Batteries are absolutely awful.
Oh yeah, we need to switch that thing. Okay, did we get there?
It was in the calc, I just didn't.
Oh, you didn't write it down. Okay, good job.
You already checked mine out.
I know, I just didn't change your light.
You changed it.
Oh, but you changed it back? You're just trying to get as many smileys as possible. So, okay, who have I? Middle table? Unit?
Oh, I put the J right there.
Oh, put it at the end of the number.
Hey.
Good job. Have smiley faces all around.
Oh wait, is mine right though?
Oh, I guess I thought you compared with her.
No.
We haven't.
Yeah, they look good. Yeah, they're good.
I did the math.
Leah's typing her last one in. Okay, so this is what homework 6.5 looks like. Okay? The biggest thing with 6.5 homework, though, is just being aware you may not use that 2,300 every time, right? Sometimes you might use that 335 if you're talking about melting a substance. So pay close attention to that, okay? All right, our next objectives are all in the same end goal, just how we get there varies. So all of them are all about calculating our delta H again. Once again, just through different means based on what's given. So our first method is we're going to be given these things called bond enthalpies, and it will help us calculate the overall delta H. So as a reminder, this isn't on your notes, but this is just to remind you, on the first day we talked about the idea of how it is always endothermic to break a bond. Energy has to go in to get the bonds to come apart. Then, as bonds are forming, so the downhill is always the formation of bonds. The overall energy, if it's exo or endo, depends on, well, did you put more in than came out, or vice versa. scientists have actually calculated the value for every single bond energy that exists that we know of. You can look through tables of them in books and on the internet. And we can find out how much an oxygen double bond costs to break versus an oxygen single bond to break. So the way I think about this is going to be our equation we're going to use, okay, is that given a balanced equation, we need to figure out, okay, how much do I have to pay to break the bonds? Then, how much refund do we get back when the bonds are formed? And the difference of it will tell me my overall energy, okay? Now, this right here, some symbols we haven't quite seen yet. So we're used to this, right? So delta H, change in enthalpy, okay? Anyone know what this great sign is?
Everyone knows what that Greek sign is.
So this is the Greek symbol capital sigma. There's actually a lowercase sigma if you didn't know. But in math, does anyone know what it means in math? I haven't heard anyone say it. There it is. The summation, right? So this means we are going to take the sum, meaning add, up all the bonds broken, and then minus all the bonds formed. Okay? This equation is not on your formula sheet. I don't know why. Okay? But hopefully it's just subtraction of bonds broken minus bonds formed. Okay? So let's take a look at a problem together. Okay? So our problem here says, what is the value for the enthalpy change for the reaction below based on the bond enthalpies? Okay? Now, this always has to be given. Okay? The table of values isn't, like, you don't have to memorize bond enthalpies. That's going to be given. This is sometimes given because you know how to draw Lewis structures. And so there are times where they don't give it to you, but you'd have to draw it to know what's being broken. Because without drawing O, if you don't know already, you need to determine, well, is it O2? Because that costs 498, but a single bond O is only 142. So you need to know what type of bond is happening. But if it's given to you, obviously that helps. Okay? So we need to look at bonds broken minus bonds formed. I'm going to highlight in different colors just to show like where these are coming from. If you also want to highlight with me. Okay? So the reactants, I have to pay to break their bond. So let's see how much we have to pay. So we have 2 CO molecules, like this, right, in this picture, and it's a C to O triple bond, so they each cost how much? 1,072 cost to break a CO triple bond. Okay, so we have to pay that money to break the bond. Pay the energy, right? Energy is money. Plus, we have to break an O2 bond. So the structure that's in the O2 molecule is a double bond. So that cost us 498. Okay, I'm going to put brackets around these because these are all of my bonds being broken. Okay, that is what is being paid to break the bonds. I then am going to subtract from the bonds being formed because that's going to be my refund, right? That's the money coming back, the energy coming out. Okay, now notice in the equation here, let me change my color, we have 2 CO2 molecules being formed. And if you look at a CO2 molecule, we have 1, 2, 3, 4 C to O double bonds. Yeah, let's see.
So we know that the O2 is a double bond, but how do we know when it's a single bond?
So that's where you have to draw it out if it wasn't given. And then the Lewis structure would tell you. Does that make sense? Okay, so I'm going to minus 4 times 799. Because these are my bonds being formed. Questions? Yeah, Calder. Once again, you have to have the Lewis structure. So right here. Does that make sense? So like when you draw the Lewis structure, it ends up being a triple bond. Because the table's showing you pretty much the balanced equation, right? The balanced equation is 2 COs plus 1 O2 So we have 2 COs plus the 1 O2. Does that make sense? Okay, any other questions on my setup? Okay, when I plug that into my calculator, let's see, did we make money or did it lose money? I got -554 kilojoule per mole is my answer. Depends on how you look at it. Did the system lose or gain?
Lose.
The system lost money, which me as a surrounding means I gained it, right? So the surroundings would take in the heat. So, questions on this calculation setup? Yeah.
So does that mean that when QCO and O2 are next to each other, oh, never mind.
Okay, good. Any other questions before I have you try one? Yeah, Calder.
On like the lowest characters, why are there like 2 on the left and right one?
Do you mean like, you're saying like why did they draw it twice? Just to match the equation.
Oh.
That's all. So, obviously if you were to do it, you wouldn't have to draw it twice as long as you recognize there was 2 of them. But, yes, like that. The surroundings took in the energy. The system lost it. So what would we classify this reaction as? Yeah, so this would be exothermic. Okay, try practice 6.7 with your table group. Once you have an answer, change your light to green, and I'll come around and check it, okay? I forgot my answer. Let me look real quick. Yes, that's correct, Lexi. Good job. Or I guess it's there we go. Oh, your light was green. I said change your light to green when you're ready. So, oh. Yes, good job. Continue on, the rest of you. Not quite.
No?
I don't know if it's a.
Ah, the 2.
There you go.
So if I multiply it by 2, then
That should be it. Yeah. Everything else looks good.
lovely.
Wait, you're confused, but you did it first.
Well done. Good job, guys. Now we're ready. Good job.
Oh, I
Oh.
got the same thing they did. 'Cause I did that.
Did you type it into your own calculator to make sure you know? Oh. That's the worst on FRQs when people have the right work but the wrong answer, so they lose all their points. Good work. Smiley faces all around.
It's sad. I'm laughing so bad.
Unit?
Same answers then. Oh. Yeah, my leg is being so
Good
dumb.
job. You're good. Keep going, Leslie. You're fine.
I did start it. It's so fun.
She admits it. Good job. I was like, why is that blank?
Where is
There's
it?
the other page. Yes. Yes. Well done. Oh, yours is. Oh, it just like skips a beat.
All 5 breathing dragons control all 5 exothermic reactions.
If you feel so inclined to change the batteries. Yes, good job. How are we doing, Henry? Typing it in? Okay.
I keep forgetting.
But you won't chemistry homework?
Yes, I will.
How are we doing, Cameron? Good. Yep, that is correct.
Oh, yeah.
It's one chemistry folder.
I didn't check you guys yet, huh?
Make sure you type it in.
Yes, good work.
Any questions in the papers is chemistry, guys.
Okay, questions on bond enthalpies? All right, next topic here, everybody. Same goal, different pathway. We're still finding delta H, but through a different means. This process uses what are called enthalpies of formation to help us determine the overall enthalpy of a reaction. So, once again, it all just depends on what the problem gives you. You can use any three method. Generally, they're not going to give you all that data. They're just going to give you one, and you have to recognize which method to use. So an enthalpy of formation is the energy it takes to create a compound from its elements in their standard states. So it's like the most basic elementary way to create a substance, okay, is through the enthalpy of formation. When honestly, most of the time, a lot of reactions can create it in other ways, but this would be creating it from its elements. So let's, just for an example to help you kind of see what these numbers represent, okay, I'm going to scroll over after you get that filled in. The little F down here, by the way, that helps us know it's enthalpy of formation. The F is for that, okay? The little degree sign is the sign we use to indicate under standard conditions. So whenever you see that, you'll see that a lot in this unit and future units. It's just saying, hey, we're under standard conditions, because obviously that changes things.
Like SCD?
Mm-hmm. Yep. So let's take a look at example just once again here at carbon dioxide. Okay, this value for its delta H represents the energy it takes to make carbon dioxide. So carbon dioxide, if this was an equation, would be the product. And we're creating it from just its elements. So it would just be carbon and oxygen. So this would be the equation for the formation of carbon dioxide, and the energy that gets released is that value. So these are another thing where you can find massive tables in textbooks of enthalpies of formation that have been determined. And so the idea is, if I know the cost of all the pieces, I can use that to figure out the change that's happening. Okay, now notice the difference here in our equation. This equation, by the way, on our last slide, I'm going to go back for a second. This one is on our formula sheet, so we don't have to memorize this one. The biggest trick is recognizing how it's so similar to what we just did, but different at the same time, okay? So in my problem here, we're going to find delta H, we need to take the sum of the enthalpies of the products and minus them from the sum of the enthalpies of the reactants. Okay, I'm going to use different colors once again to help us out here. So my products are carbon dioxide, and notice I have 6 of them. So I'm going to do 6 times our negative 393.5. Plus 3 times our value for water, negative 241.9. I'm going to put brackets around that to show, hey, these are all my products together. And then I'm minusing the reactants. So my reactants I have here is we have C6H6, which is right here, so that would be 82.9. And then, oh my goodness, they didn't tell us oxygen's value.
No.
What are we going to do?
Nothing. Just skip.
Why is it not there? Why does oxygen not have an enthalpy of formation?
Maybe because it's 0.
Why is it 0, Mason?
Because it was never part of the reaction in the first place.
Ooh, no, but nice try. I have a smiley face. Lila? Because enthalpies of formation, everybody listen to this. Say it again, Lila. Can you form oxygen from elements? No, oxygen is an element. It can't be formed from elements. And that's just how it exists, right? Like it's just here.
Because this one says
in the universe, it just exists that way. Now, you can believe where that came from a deity or the Big Bang, but nonetheless, it just exists that way. And so all pure elements have an enthalpy of formation of 0, which sometimes they show you on the table, but sometimes they don't.
That's what I found.
Does that make sense? Okay, plug that into your calculator. Let it do your work. And I got
Is that a 0 or is that an O?
a 0. That's kind of confusing because it is oxygen. I was putting in a 0 just to like emphasize the point. I got negative 3170 when I round for significant figures. Questions on my setup or process before I have you try one? Yeah, Stephen, then Will.
So what does this find compared to what we did in the previous one?
It finds the exact same thing.
Is it just
It's just a different way of finding it. Last time we found it through using the bonds of the individual pieces. This one we're using the values of the whole thing. But actually, if you had both sets of data, you'd get the same answer.
So what is this, like, the value table, what is that telling us?
So that's telling you that that is the heat cost to form CO2. The reason why, like, the equation is backwards from what we did before, right?
So before it was how much you get from breaking it, and this one is how much it costs to put it together?
Kind of. But now in a case of it's like, that value is being put together for everything, but in the end, am I putting these together? These are being put together, and these are being taken apart, right? So that's why we minus theirs away. Does that make sense? Because it's like going in reverse. So that's the confusing part about this once again. The homeworks, because they're broken up, I find a lot of times students are fine, because when you do just one thing at a time, it's like, okay, I got this equation, I can repeat it. But then when the AP test comes and it's all mixed together, the trick is recognizing, oh, this is the formation process versus this is the breaking bonds process. Because they're similar but different enough. So, does that answer your question? Thank you. You actually helped me like find a better way of saying that than I did last period. Yes, Will.
So there's 2 oxygens. Is there a reason why it's still 0 is because it's diatomic?
Yeah, like that's its elemental form, right? That's just how it exists.
So you have like 2 bonded and non-diatomic.
Yeah, so theoretically, if you had something, let's say like, so phosphorus can exist as just P, but it can also exist as P4, but P4 is not its natural form. Technically, it would have an enthalpy of formation value. The nice thing is, though, it's going to be given if it's not 0. So, yeah, good question, though. Any others? Okay, try practice 6.8 with your table. When you're ready, change your light. Is off our next? Are we around the circle? Turn it off, and I'll come around and check it.
I need to know the speed of this.
Whoa.
Wait, Sean being such a cheater.
Yes! Good job. What are you doing? Don't give it to them. Make them think.
I was trying to ask to confirm if this was.
Oh, well, they haven't written anything yet.
I'm making them think by looking and make sure what I have is right.
Yeah, you got the first part right at least.
That's funny. Is it like extremely negative 65?
No.
No? Wait, but there's 2 of these, and that's 0. And then you add 3 of the CO2.
True
And
statement.
then you minus the FeO3, which is that, plus the 3 of the CO.
Yeah, that's what you're supposed to do.
Yeah.
I don't know
Then you have
what.
that,
Did I get it right?
and then minus literally the same format that I have here.
Did I get it right?
No.
Oh. Wait, I was right.
Wait,
I'm trying to see where the math went.
wait,
Did you
No, I
catch
was
it?
right that she got it wrong.
wait.
Oh,
Negative 23.
that's the answer.
23.
There we go.
Stupid freaking coefficients.
Yes. Good job. So is it endo or exo?
Have to kill me.
Exo. Good job. Once again, when you're ready, tap your light off and I'll come check it. Not quite. Let's take a look here.
Every mole of reaction, so every time this happens, a mole now.
You have it backwards. These are reactants. No, wait, never mind.
So you have
I don't know. What's going on here? Oh, you put the wrong value in for CO2. You looked at CO on accident. That's tricky. That's tricky. Not quite. So let's glance. This looks good. This looks right. Try that again. Yeah. But your setup looks good, Henry. Unit. And it should be negative.
Negative?
How did you have it? Oh, you did yours. Did you do it backwards?
No,
Oh, yes, you did, because it should be products minus reactants.
Products. I thought that's what. Oh, okay. Wait, I swear.
So it should be
Oh,
products.
oh, okay.
Does that make sense? Flip it around and make sure you get it.
Colleague I did it. Oh. Because I think I did it. No?
Wait, am I right?
He got 23.
That's what it is.
What? Oh. No.
Wait, what did I do wrong?
Oh, yeah, it's negative.
Yeah.
I'll come back. Yes. I was like, wait, how do I guess I just also say C. Good job. Oh, wait. Yours is backwards. It should be products minus reactants. So the equation is products on the left, and then your but you did. Do you see that? Because you did your reactants. You like lined it up with the equation. Do you see that, Marilyn?
Yeah.
So flip that, which ends up making it a negative 23. So, yes, Eddie.
It's the energy that it takes to create these minus the energy of what's already there, like what's creative of what's already there, I guess.
Yeah, or in a sense, because the enthalpy of formation, if you think of it in reverse, which is what you're doing when you're minusing it, would be like the energy to take it apart.
Okay, that makes
Does that make sense? So that's why it's kind of like bonds broken, bonds formed, but we're not looking at each individual.
You're just like looking at the molecules.
Yeah, yeah. So, does that help?
Yeah, would the total thing bonds formed be like add up to, or would the bonds, energy to break the bonds be the same as like the total energy?
Well, that's an interesting thought.
Or is it,
Like if you added up all the individual bonds in a molecule.
yeah, or is it,
I don't know, Eddie. I'll have to ponder that.
I don't know.
I don't feel like my initial instinct is no, but I don't know why.
I don't know. It is because, yeah.
But yeah, that's an interesting thought. Next year I should almost make one of these exercises though like the same equation. So you can see like you'll get the same answer. But yeah, individually I'm not sure.
Maybe 2 grams instead of grams.
Yes. We all agree?
Yes.
Good job. No. No. Do you all agree on this wrong answer?
Yeah. Is it wrong?
Yes.
Oh, cute. Wait, so we're supposed to do the other
Did we calculate it right?
I think it's a math error. Your setup looks fine, but that's not the right
We're all
answer.
using
You're blaming Gavin's calculator. We'll try typing it again. Something's off. Did you get 23, Rachel?
Two numbers in here. My calculator is being so stupid.
You're saying 1 mole of
Good.
the
Negative
reaction
23.
has 6.02 times 10 to the 23rd of this.
Did we get negative 23?
No. What?
Did you get it this time? Make sure the biggest thing, so yeah, 2 times 0. Okay, keep going. Show me what else. Can you show me what you typed?
No, this isn't 0. This is 0.
Okay, you're going to want a second parenthesis on this grouping, kind of like to show the brackets. Does that make sense? Or maybe not. Okay, keep going. Oh, I don't know why it's being weird.
You're like, it's so calming.
I don't know either. I can't tell from your calculator, but your setup's right. I know that. I'm not sure. I'll have to look at it and see what is being... Oh, it's a negative 826. That's it. Did we all agree now?
Yeah, it's not even 23. We all just did that stupid.
Okay, how are we doing on time? 15 minutes? Okay, one more way to get to delta H. Are you ready?
there's so many though?
I don't know. I guess just depending on what you have, and they should just pick one and be like, this is the best way, and just do it this way.
People just wanted their minute of fame, so they made
Probably.
all those different ways.
Because they're like, oh, well, someone hasn't done it this way yet. It is negative. Okay, our last method, everybody, give me your eyes up here. Once again, we're still getting to delta H, just the means of getting there is different. This way takes into the concept. So the first way, once again, was looking at bonds broken minus bonds formed. The second way was looking at them as a whole and being like, okay, we're going to form these. These are being unformed, is the way I think about it. And so what's the overall? Hess's law is a method of using steps, okay, and saying, okay, well, if I know the steps it takes to get to my product, then I can add up those steps and it will tell me the overall cost. Okay, that's what Hess's law is. So it's going to have a very similar look to mechanisms. The difference is mechanisms are always in order. Hess's law, we have to put the steps in order. Okay, that's the catch. So with Hess's law, once again, it's the idea that if you add up the steps in an overall, they will equal the overall heat of the reaction. Okay, so Hess's law is this process of you're going to be given the steps, you don't have to make them up, but we're going to have to rearrange them so they become what we want them to be. Once again, here's kind of a visual to kind of help you see that once again, of to get from here to here, we know these steps, and so then if I add those steps together, I know straight across what it will be. Now, there's a few things with enthalpy we keep in mind as we rearrange our steps, and then we'll do a problem with it. Okay, so the first thing with Hess's law is that heat is an extensive property, meaning if I double the reaction, then the heat will double. Right? We mentioned this before. If I eat more Cheetos, yes, I'm going to have more energy, right? Because it just has more in it. If I put more wood, I'm going to get a bigger fire. Okay, so it's an extensive property. There are certain properties that are not. You can add more, and it doesn't make it higher. We'll learn about that actually in Unit 9 with electricity. It actually doesn't make the battery more powerful, it just makes it last longer. Yeah, Calder.
I thought that enthalpy was the energy overall.
Good clarification. So notice here in my answer, okay, that I'm not, in terms of so I'm just using the word heat. Okay, so I'm not talking about enthalpy, I'm just talking about the actual heat, because you are right. If I do the ratio, it's going to balance out. Totally right, Calder. Good reminder. Have a smiley face for that. Okay, a second property is recognizing that if it's exothermic in one direction, if I do it in reverse, it's just going to be flipped in sign. Okay, so if we need to take a step and we're like, oh, this step is backwards, we need to reverse it, then we're going to reverse or flip the sign of the enthalpy. And then the last one, we don't use it that often, but it is important to recognize, is that enthalpy is dependent upon states of matter. So gaseous water is not the same as liquid water when it comes to their enthalpy values. So just paying attention to the subscripts matters. They're not the same thing, okay? Here's the basic steps that we're going to use to follow Hess's law. I'm going to kind of refer to this as we go through that first practice problem together. Okay, the biggest thing is you you know the goal. You know what the overall reaction needs to be. We then just need to change the steps so they add up to that overall. So the biggest place I've seen students get confused is if they don't keep their eyes on the goal and they focus on the distractors instead, you can get really lost. But if you focus on this is what I want, everything else will just work out. Okay? I'm going to do step number 1 here in red on our first problem, and I'll come back to this. So step number 1 is to flip any equation if needed. You may not need to, but if needed, to get the reactants where they need to be and the products there need to be in relation to the goal. Okay, so let's take a look at this problem and do step 1. So this right up here, this is the goal. I want it so that when I add up these 3 reactions below, they add up into that reaction. Exactly, meaning we get rid of everything that's not there and everything's in the right place. So, focused on the goal, I see carbon needs to be a reactant. Which step gives me some carbon? Pure carbon. Good. Step 2. And it's on the reactant side, so I do not want to flip step equation 2 around. Okay? I'm going to leave it as is. I'm going to rewrite it just because it will help make it a little cleaner to know I'm keeping it as is. So I'm going to take my equation and I'm going to rewrite it down here just the way it is because I don't want to flip it, which means I'm going to keep the delta H the same. I'm going to show you quite a bit of writing on this first one to help make it clear of the process. Obviously, the more you do and the better you get at it, you can somewhat simplify and not have to write everything as much. Okay? All right, my next piece I need to keep, I'm going to use different shapes just to help my mind. I'm going to square H2. I need H2 to also be a reactant. Which equation gives me some H2? The third one. And we want to keep it as is because it's a reactant. Okay, so I'm going to write that equation right below. I'm a big fan of lining up your arrows as you rewrite because it will really help you see what are the reactants and what are the products. Okay, and then that means I'm going to keep my delta H as is. Steven, did you have a question?
Why does it say 0.502 instead of just O?
Ooh, good observation. I forgot to introduce this because I don't think we've seen it before. You're allowed to have decimals in a balanced equation because it's just a ratio, and so 0.5 just means you have half a mole of that substance. So, yeah.
But would it just be O, or would it just be...
It's actually, it's O2, but it's just half a mole of O2.
Oh,
So, yeah, good observation, though.
right that instead of just 2 ratios from the plus O2 plus. It just simplifies the other things more.
Yeah, like, so you could, instead of having a decimal, it could be 2 and 2 here,
Okay.
right? It'd be the same, but, yeah, Ray.
Should we not write the subscripts if it's like a gas or liquid?
Being right now, I guess I'm skipping that portion because I recognize, like, there's no differences. There's not, like, one gaseous water and one liquid water. But if you did notice that, then you would probably want to write it because they wouldn't, like, cancel with each other. So, yeah, good observation, though. All right, and then the last piece I need is I need C2H2. I'm going to do a squiggly line here. Okay? Which equation gives me that? The first, and is it as written, or do I need to flip it? Yeah, we need to flip it because as written, it's a reactant, but I need it to be a product. So I'm going to flip equation 3. And so I'm going to put 2 CO2s, our H2O. Once again, I like to line up those arrows. C2H5 and 2.5 O2. And then that's going to do what to my delta H?
Where did H5 come from?
Good question, Mason. You know what's so weird? I did the same thing last period. I just really like C2H5, I guess. It's propane, so. Okay. 1299.6. Okay, step 1 is done. Because I put the 3 things I needed. So I needed carbon, I needed hydrogen, and I needed C2H2 on the other side. Okay, going back over here. Whoa, too far. Step 2 is, if needed, check to see if you need to multiply one of the equations so it matches the goal. So looking at my goal reaction, I see that I'm going to do this one in blue. I see that there's 2 carbons in the goal reaction. But in this equation, it only gives me 1 carbon. So I'm going to multiply everything in that equation by 2 so that it matches the goal, which means I then am going to multiply its heat by 2. The other 2 are good because I only need 1 H2, I only need 1 C2H2, so now I'm going to check and see if I did it right by adding up my reactions. This is where it's like mechanisms. If something appears the same on both sides of the arrows, they'll cancel out. So who gets canceled out when I add up these 3 reactions?
CO2.
Good. So AJ noticed that there's 2 and 0.5 oxygen on the left and 2.5 oxygen on the right. So oxygen gets canceled out. Cameron, what else did you notice? Good. CO2, there's 2 of them here and 2 of them there. And good. Our water gets canceled out. And if I rewrite what didn't cancel, does it match our goal? We made it to the goal, which then means that's not our answer. Our answer is add up the heats, because that means everything's in its appropriate order and amount, which I got. So when I added them all up, agreed. Yep, 226.8 kilojoule per mole. I don't know how to explain that actually, AJ. I just know it's always kilojoules per mole for your final answer for delta H. I don't think they marked it wrong if you just put kilojoule, because it is labeled as delta H.
Wouldn't the reaction, I feel like if we're doing 226.8 kilojoules per mole, and like our units up there for delta H should be.
That's what I'm wondering too, if those just got left off in the first place. They're delta H's, so yeah. But any questions on the process? Thanks, AJ. Of Hess's law? Yeah, Mary?
So,
We just got like 90 seconds left here.
so why did we take anything out of the, like, things, or did we just add them all?
No, so the idea of doing this is once this gets to here, it tells you just to add them up. Because that means all the steps are in the order they need to be. Does that make sense?
Wait, so the only thing we changed out it was just multiplying that one by 2?
And we flipped this equation. So this equation got flipped. That equation got multiplied by 2. So, yeah, Nathan? And it would be endothermic, yes. Michael?
So for multiplying 2 for the negative 3 times 3, you multiply that 2, so it becomes positive.
It doesn't become positive because it's 2 times negative 393. So it stays negative. Does that make sense? Yeah. So the only time the sign changes is if you flip the equation. So.
Right?
Say it again.
Is the test on Thursday next week? Yeah. Does that mean this was our last lesson? Because the next time.
What?
Yeah, it's a baby of a one when we come back.